Hey, cast and friends and Professor Nicholson um, and everyone. It's an honor to have you here with us tonight. This is a special lecture in our series that we weren't quite sure would happen until just a few weeks ago. Our speaker tonight is Dr. John Church, and that surname will probably seem familiar to a great many of you. For the 12-inch refractor in Fuertes, the Fuertes Observatory's dome, named for former Cornell professor of civil engineering, Irving Porter Church. When John reached out to us about this study that he'll be presenting tonight, he reached out to us last semester. None of us, John included, had any idea about a connection between him and Professor Church. As it turned out, by a remarkable coincidence, there is one, which I'll let him tell you about. John is a former director of the Amateur Astronomers Association of Princeton. He's been with the organization over 50 years at this point, and my understanding is now they call you an emeritus director in Princeton. He's a chemist by training with a long research career, but more recently, I say recently, still for a long time with many articles under his belt. He's been an expert in optics, publishing articles in Sky and Telescope and performing optical analyses, not only of the AAAP's 6¼ inch refractor designed by the famed Charles Hastings, who worked on our own lenses, but also the 40-inch refractor at Yerkes Observatory, which has a provenance remarkably interrelated with the Church refractors lenses as well. That 6-inch refractor in Princeton is now housed in a New Jersey observatory that Dr. Church helped build in the 1970s. And we're happy he's been able to make it this week. He visited Fuertes Observatory last night on the clearest night we've had for some time, very close to a new moon, I might add. And he had a look through this telescope that he has conducted a provisional analysis of, and assured me that it is, in his words, a very nice telescope, which is a relief to us all, I think. Please join me in welcoming Dr. John Church for this very special lecture that we could not be more excited for. Thank you for coming.
Okay, Ben, thank you so much for that very kind introduction. People may be wondering, how did this all come about? Okay, I did write some articles in Sky and Telescope some years ago about the optics of refractors, including the one that we have, which has a very interesting relationship to the one that you have, and I'll get into that. So I was browsing on the internet. I wanted to see what other institutions had telescopes that maybe I could just take a look at and see how they were doing. And so I just checked Cornell. Okay, does Cornell have a good one? You bingo. Okay. And they not only a good one, they've got one with my same name, which is a total coincidence. And it's not well, it's very interesting because his wife, I know his wife actually is or was my fourth cousin 3 times removed. And her middle name was Porter, and his middle name is Porter too, and I have Porters in my family. So as I say, that plus a ticket will get you on an airplane. Okay? But anyway, so it's a kind of an interesting link. So I was like, I got to learn more about this telescope. So I wrote to the society, and Ben very kindly answered my emails. And one thing led to another. And so I was trying to figure out the optics of this telescope, if I could. It's a long stretch. At first, you've got to know the kinds of glasses that are in it. Nobody seems to know that, but we have a kind of a guess about it. So we'll start from here, and I just go over a few things. Let's see, it's not advancing. I'm hitting this.
If you try click.
Uh-oh, it doesn't
Mr.
advance.
Shapiro, could we have your assistance, please?
Oh, frozen screen.
First slide.
First slide, freezing. That's it, folks. Thank you.
Good luck. That's the way to go.
There we go. Now we'll do. Okay. So what we're going to be talking about is geometrical optics. There's geometrical optics and there's physical optics. Physical optics It's much more complicated than geometrical optics. But with the concept of a light ray, which is kind of a fictional concept, you can use the concept of a light ray to design an optical system if you have the right equations. So this is basically how refraction works. Light comes along and hits glass. It's like a speed bump in the road. It slows down and gets deflected. And that's why refractors work. You could also think of wave fronts as another way to look at light. And a ray is like perpendicular to a wave front. A wave front hits the glass, and the glass slows down the wave, slows down the speed of light in the glass for many reasons. And so it's like that. So basically, that's the basis. There's a common slide. I like to show it. It's from an old physics book. How the telescope works on an extended object like the moon. And so this is why you get an inverted image. It turns everything upside down. The first time people get a telescope and say, why everything's upside down? And so, but this is how it works. And you get a real image. I don't know if you've ever tried this. If you take the eyepiece out of the tube, and you've got a real image floating in the air there that you can see. Have you ever tried that? Take the eyepiece out and look, you'll see. So all the eyepiece does is it's like a magnifying glass. You magnify the image so you see the details. So that's basically what I'll be talking about. Now, your lens, okay. It turns out that Charles Hastings, who designed your lens, also designed the lens for the Sproul 24-inch refractor at Swarthmore in Pennsylvania. And that one's twice as big as yours and probably 8 times heavier. It goes as a cube of the size. So anyway, but this is a design, this is a drawing in the article that he published about this refractor. Your lens is basically the same shape. You've got the flint in front and then the crown, and they're basically, from what I'm gathering, they're basically almost in contact. There's a small space. The light comes from left to right. And we know, by the way, I never asked this question last night. Do you know that, and this is, I'll put you on the spot, do you know that the focal length is exactly 180 inches? Or is that just an assumption? Do you know, because I'm using that, but sometimes they say, oh, it's F15, it's 180 inches. But you can measure that by doing a photograph, getting the image scale. So I don't know, did anyone ever actually determine the focal length? I tried to put you on the spot. No, but anyway. Okay, so anyway, you can do it. If you take a photograph using direct objective, where you put something there and record it, and you notice image scale, from that comes the focal length. So we're going to assume it actually is 180 inches. Close enough, F15 is close enough. So that's what your lens would look like if you sawed it in half. Hopefully you'll never do that. Please, don't even take it out. No, and now, a few months ago, I gave a presentation at our club about the Yerkes Observatory telescope, the big 40-inch, a huge baby like that. It's a totally different design. It was made by the Alvin Clark Company, famous telescope makers of long ago. And in this case, the crown is in front, and the crown and the flint are separated by more than 8 inches. And they did that, so they put access holes in the cell so you could reach in and clean the surface very gently. And also to help with the cooling, because a lens this big and heavy, it doesn't cool. It takes all night to cool down. And even if you've got these holes in there, the thing is so big and the glass is so heavy that it just takes forever and ever to get it to cool down. And sometimes mirrors are even worse. So they put in spaces there so they could do that. Now, when you do that, it almost looks like a telephoto lens. You're pushing the flint back. It pushes the second principal surface out a little bit. So the focal length is larger than what we call the intercept distance or back focus, which is measured from the back center of the rear element of the lens. That's the distance that you measure the aberrations from. You don't, I mean, the focal length is good and you need to know that, but as far as all the aberrations, you got to know the back focus and how that changes with the image height, the ray heights, and all other things that I'll be talking about. But anyway, this is a totally different design, completely different design. Yours isn't anything like this, but I have a suspicion that yours is better than this. I'll tell you why. Maybe it is, maybe it isn't. So you're going to use this telescope visually. So it's nice that we have a visual sensitivity curve for the human eye. It's really most sensitive in the middle of the visible spectrum and the green and yellow areas. The sensitivity drops way off the red and the blue areas. It doesn't look like it. You look at things, the red looks just as bright but it isn't nearly as bright. So it's good to optimize your lenses so that you have the best corrections in the middle of the visual spectrum. That's very important. Now, when you're dark adapted, like astronomers are, this curve shifts a little bit to the left, and you get what's called scotopic vision instead of photopic. So supposedly, as astronomers, we all get dark adapted. So the sensitivity is going to shift a little bit. But if you look at the moon, and then there goes your night vision, and then back to square one again. So it happens all the time. The moon blinds everybody. So anyway, we'll be talking about achromats, color-corrected doublet optical elements. So years ago, how to make these double objectives. They used a single lens, and they built these enormously long telescopes to cut down the chromatic aberration. So you see, with the single lens, you get this straight line relationship between the wavelength and the intercept distance. So it's you get the shorter wavelength for violet light and a longer wavelength for red, and nowhere is it any good really. So all these things is color fringes all over the place. But in around 1730, they invented the achromatic lens, where it brings both red and blue light to the same focus, and in the middle, in the yellow, the curve is pretty flat. So that's what you want in a visual telescope. So that's where your eye is sensitive, and that's where you have the less aberrations in. That's the kind of lens that you have. And in fact, everybody. Well, now there are triplet lenses too. These days you can buy nice triplets, but even better. And even in the old days, you could do that. They're more common now. So what do you got to worry about? If you have just a simple convex lens, you get spherical aberration. The edge rays come to a focus a lot closer than the central rays. And this is okay, you're going to get a fuzzy image. But if you use the double objective with the crown and the flint, you can make the flint element neutralize what the crown element did, and you can wind up with very little spherical aberration, which is what you have. Your telescope is really very well corrected for spherical aberration. That was Hastings' strong point. He did a good job. All the ones that he designed had very little spherical aberration. They still have chromatic aberration. You can't get totally away from that with a doublet objective. So the next thing we'll talk about is the real baddie. It comes to professional work. It's called coma. And so many large telescopes have substantial coma. It really bothers them. It's when different zones of the objective have different focal lengths, and you get a smeared out image with a point and a spread. You get what they call flares out. This has been a terrible bugaboo with some of the large refractors, as all because the people who made the big refractors did not take into account that this is what they would have if they did not pay full attention to the design parameters. They like to make the inner radii of the doublet the same for manufacturing reasons, because to do the best work, you want 4 different radii of these elements, R1, R2, R3, and R4. But for reasons of economy, they made R2 equal to R3, and you didn't have to make another set of tools. So when you do that, you're going to, in most cases, get some coma. This has been a horrible problem because the large telescope did parallax work, to determine the distances of stars that are not too far away, where the Earth in its orbit, you see the stars shift a little bit against the background as the Earth goes 6 months in, 6 months out. But you got to have a comparison star in the background to measure that shift. You have to have a comparison star, and you make the assumption, usually with good reason, that the comparison star isn't shifting very much. So it worked for nearby stars like Barnard Star, even Polaris, a few others are fairly close by. But if you get this kind of effect, they don't know where the comparison star is. And they invented several different ways to try to compensate for that. They put neutral density filters up. They put a diaphragm in front of the objective. And the cute one that I saw in Pennsylvania at Sproul was they had a rotating sector. They had a circle thing that they put near the eyepiece. It had a sector cut out. And they spun this thing at high speed. And what that would do is dim all the stars. And so you know where the central star was, but you wanted to dim the comparison star enough so you didn't see this flare. So that's what they did. So the thing was like this, and they would dim it down. Then they could get a better measurement. it still was a problem. But they actually they built their reputations on measuring accurate parallax. And in a lot of cases, and sometimes it worked, but because they had this aberration, it could have been removed if the makers had taken the trouble to do it. Could have been. They didn't do it, and that's an ongoing problem, and they have to live with that. We'll talk about some of the glasses. This is just a table of the refractive indexes of all these different glasses I'll be talking about. Now, I put the Yerkes crown and flint first because we know those indexes. Now, I have made a leaping assumption here that you have the same glasses that went into the Yerkes refractor. And I think there's some sufficient, maybe good reason to believe that, because the blanks that your lens was made from came from Yerkes. They were shipped to here from Yerkes because Yerkes knew, the people at Yerkes knew that you wanted a telescope. They had these leftover 12-inch blanks that they weren't using or they weren't going to use. And they apparently had gotten them at the same time that they got their own blanks. And they were sent to the Alvin Clark Company in Massachusetts that made them. I have made this leap of faith, and it's just a leap of faith, that your glasses are the same type as the Yerkes glasses. It may not be right. I hope it is, but it seems to work. Okay, you use these glasses, it seems to work. So but someday somebody may prove me wrong, and that's fine, because no one knows where this glass came from, really. But I think there's a really good chance that it's the same as the Yerkes glass. And if it is, you'll see what happens. So I put these down. Also, the glasses for the Hopkins glass that Hastings also made, and our own that I'll be talking about. So these are the kind of parameters that you need when you want to do the analyses. So how do you design a two-element lens, an achromat? This is a classical method, and even Hastings used it. You start off with a focal length. You say you're going to specify 180 inches focal length for your telescope. Fine. And you have to select two glasses with different V numbers, or what they call constringencies. You've got to have quite a difference in their ability to refract the light in order to make a decent lens. So you got two very simple equations that everybody knows how to solve in high school, two simultaneous linear equations. So the two equations are the focal length equals 1 over the power of the first lens plus the power of the second lens. So you specify that. And then you want to find P1 and P2 is what you want to do. You need another equation to do that. You got to have two equations. So it turns out that P1 over V1 plus V2 has to be 0. A very simple pair of equations. You can solve them easily. So I did that here with this. So using the Yerkes glasses, I put as an input 180 inches, and V1 the Yerkes one, and V2 the Yerkes V2. So if you do that, you get this output: P1 and P2 equals such and such. So you add them up and take the inverse, and you get close to 180 again, just to check if you did the algebra right. So now what I've tried to do is make an approximation as to what your lens curvatures are. And I think, I hope it's reasonable, but it seems to work. It does seem to work, and I'll get into that. So to make the story short, my provisional values for P1 and P2 are down here at the bottom. And if you add those up, take the inverse, you still get 180. So it's that's how it works. So everybody uses this. Yes, question.
Again, what B1 and B2 are?
Yes, yes. You see back here at the slide, the makers determine this.
Oh.
Okay, so the V1, these are the index for sodium light -1 divided by the difference in the index for blue light minus red light. Okay, so those numbers are different for each glass. Okay, so you take like
measuring the wavelength.
Yeah, see, they do this when they're manufacturing. They make prisms, and they have they can determine what the refractive indexes are and the V numbers. So they send these numbers to the lens, because the people who make the lenses need to know these numbers if they're going to design the lens. They have to know that. So the makers know it, but they usually don't publish it. They don't like to give away their secret. So when they make the maker always knows what these numbers are. Otherwise, they can't design a lens. They can't make the lens. So they have to know that. So they're known, but they're not published in those cases. They're so secretive. Well, you can blame them. They're in a business. They don't want to tell their competitors what they do. So they kept them secret most of the time. And they even sometimes gave false information to the astronomers to throw them off. They didn't want anybody to publish this stuff. They said, okay, you wanted a lens with this focal length here. We gave you one. Be happy. That's it. We're not going to tell you any more about it. It's like you buy a car. They're not going to tell you, and they're not going to tell you what engine you have. They're not going to tell you. But this is the way they operated. There weren't very many of them, so they wanted to keep their trade secrets. So anyway, so we're back right here. So what I did, okay, you buy a piece of software. They're telling you, do not reverse engineer the software. Do not decompile it. Don't do anything. Take the software and use it. Now, we got this old telescope. I don't think anybody's going to bother me if I reverse engineer your lens and try to figure out what it was. So I've tried to do that. And this is how I tried to do it. We were very fortunate that Hastings, who designed this lens, published full details of the 9.4-inch lens that he did for Johns Hopkins. He published it in 1882. And everything, he published the refractive indexes, the radii, the spacing, everything. So that was his model for making lenses. And so the good thing about that, by publishing that, he established his reputation. And the Brashear people in Pittsburgh found out that Hastings knew his stuff when it came to lens designing. So they hired him as a consultant for 30 or more years. They hired him. And he designed all of their lenses, including the lens that you have. So I said, okay, we're going to make a stab at this. I said, okay, suppose we do have the Yerkes glasses. All I'm going to do is scale up the parameters for the 9.4-inch to 12-inch. You can do that if you know everything. They scale directly. So I did that, and I put them into my software to see what came out. And it came out that the focal length was not far off from what you do have, but just by scaling the radii that he had published. So I had to adjust it a little bit to make it work. So I made the space smaller because we know it's pretty small. And I made R2, the second radius, equal to the third radius because that's what they all did for manufacturing reasons. I think it's a reasonable assumption. They didn't want to make 4 sets of 2. They just wanted to make as few as they could make. So they did that. And as a result, they did get some problems later on with Coma. But so then it got pretty close. And so all I did, and this is a common thing that they did, they changed one radius to get to the right focal length. So that's what I did. I just changed R4 down a little bit, and I got the focal length that you have. So I said, maybe this is going to work. So these are, I'm going way out on a limb here. These are the radii I think you might, if you ever measure these things at some future time, compare them with these numbers and see if they're right. They may be right, they may be wrong, I may be full of hot air, they may be not even close, but I have a guess that it's going to be something like that. So the result came out, the focal length is a pretty good match. The spherical aberration is essentially zero. And it does have a little bit of coma, according to the math. In other words, what they call the offense against the sign condition is 0.0014. Now, if it's 0.0025, that's the maximum that people like Conrad, he said you shouldn't go any bigger than that. Otherwise, it's not going to look good. So you may or may not have this degree of coma. Now, last night we put it on, kindly put it on the double cluster. I couldn't see any at low magnification. I think maybe it might even be better than I think it, I don't know. But if you can get a photograph on a good night of a double cluster at a large scale, and you can look at the star images and see if there's any fuzziness there. There may not be, in which case you got an even better lens. Okay, there might be a little bit. So my conclusion and my speculation is that Hastings did this all the time for the Brashear Company. They never made a lens without his say-so. He was the math guy, they were the lens guy. And so I think what he did, if I can speculate, is all he did was use his template for the smaller lens, take the glasses that they had and plug it in and scale it up and charge them whatever he charged them over and over again. Not bad work if you can get it. So nice guy and very talented, but they didn't know how. The Brashear people did not know how to do this, and he did. So that's the key to being a good consultant. You know how to do something, then the sky is the limit. So I think maybe this is exactly what Hastings did. I don't know it. I don't know it. But we'll go into this. So here's some what we call color curves for this this lens with these radii. This shows the back focus as a function of the wavelength of the light from blue to red. And it would you see the usual kind of curve you get with an achromatic lens. You get red and blue light coming to about the same point in focus. And here, if these are the radii, you have no spherical level. You have none. So small it doesn't matter. That you would be allowed to reach what's called the Rayleigh limit of a quarter wave. You could have as much as 2 millimeters of spherical aberration, and you'd still come under the quarter wave assumption that Lord Rayleigh can. This is like nothing. This is like nothing. So if these are the radii, and this is one of Hastings' trademark. He did this right. Yeah, and I don't think you don't have any spherical aberration. I don't think so. That's what would come out. That's what comes. Let's hope it does. So we know all these refractive indexes because the National Bureau of Standards measured these for the Yerkes glasses. So again, I made the leap of faith that you have the same glasses. So and it's fitting. It's fitting. So let's see what happens. So my friend Matt Considine had a very nice piece of software called Oslo, I think, optical software for lens optimization. A very expensive piece of software. I think you can get a trial version of it if you want. So he made these spot diagrams using Hastings' own published values of the glasses, the indexes and the radii. So if you're on axis, you see it looks pretty nice. Now what you're seeing there, the red areas of, it's as much brighter than it would actually appear. That's where the red light would come to focus. In the middle, there's a little black circle, and that's what they call the airy disk, the diffraction. You get the diffraction effect at the edge of the objective. But you know there's no spherical aberration because what's inside the airy disk does not extend outside of the airy disk. In other words, it's diffraction limited, which is what you always want your telescope to be limited by diffraction, which you can't do much about with a given size, because you get diffraction at the edge of the objective. Can't do that. The bigger it is, the smaller the area it is, and then more double stars. But look what happens off axis. If you go a half a degree off axis, the thing gets not good at all. And you're seeing the coma there. You're seeing the coma, and you're seeing the outward. You can see it. Don't worry too much about the big spread, but you can see the flare outward, and as you go way off axis. So this is from Hastings' own data and applied with the Oslo software. So this is why it has coma off axis, and you might be able to see it, you might not be able to see it. So we'll compare this later with some other spot diagrams. So Mr. Considine was very kind in doing this for me. He had read some of my articles, and he did this analysis for me. I really appreciate that. So now, what happened later? Okay. It's nice if you can correct both spherical aberration and coma. And if you do that, you get what's called an aplanatic lens. It's from the Greek, means not wander. A for not, and like planets wander. So the aplanatic lens is lens that has no spherical aberration and no coma. This was done in the 1760s already, and it was forgotten for a long time. Two scientists I'll talk about, Clairaut and D'Alembert, did it and published it. It's very complex, but they did it. But the equations were so complicated, the opticians couldn't read them. They didn't know how to do the math. They couldn't. So they went back to their old empirical methods of grinding the language. And they just totally ignored this groundbreaking thing. Excuse me. Now, in 1887, there was a German engineer named Karl Moser who, apparently without giving credit, published these equations again. And he didn't even reference the word, but the exact same equation, the exact same equation. He could not have made them up. He could not have made them up. So he published those. And then in 1935, another German scientist, Bodehold, discovered this, and he wrote an expose of what happened. And he said, these are the same formulas that were published in the 1760s. Well, but everybody else was. This was not a great thing that he did. But you got to have, to do this, you got to have 4 separate surface radii. You can't have R2 equal 5. It's not going to work. So that's the key. In the 1820s, Joseph Fraunhofer in Germany, probably you know Fraunhofer from the Fraunhofer lines of the spectrum, made some really fine lenses. And we don't know whether he knew about the French work or not. We don't know because he never left any record. But he made some wonderful ones. And they work well. They still work. Some of them work well. We are very, very fortunate ourselves in having a 6 1/4 inch objective mounted on a telescope that we have in the astronomy club. I'll go into the story of that a little bit later. Hastings used the Fraunhofer model for this lens, and it does have 4 different radii. And that's why it's a pretty good lens. He made that in 1879 and published some of the specs of it. The other specs were hidden in some of his notebooks, which I researched out a bit. And what I did, I had custody of this telescope for a while. It's a long story about the history. The astronomy club wound up with this magnificent unused telescope, 6 1/4 inch refractor that nobody wanted. And they had to find a new home. And at a meeting, the director said, so we need to have somebody take custody of this old telescope. Who wants one? Yeah, I want 6 inch refractor. And I have a fat city. And I say no. So I got the thing and I cleaned it up and actually measured the radii, and I'll talk about that. It's a terrific lens and it's still in use to these days. The Alvin Clark Company did their own designs in-house, very simple designs. And they made the crown lens have R1 equal to R2, and sometimes even equal to R3 for manufacturing reasons. They're pretty well corrected for spherical aberration. They have coma. And other people have written about this. They say it's a pity that these refractors have coma because it hinders us when we're doing the parallax work. We can't do that. So it has good central performance, but coma was left to chance. And the Brashear people who had made your lens, they used Hastings designs from 1887 on to the mid-1920s. And for a long time, they did that. They never made a lens without Hastings having checked off the design. And the reason he puts the flint in front, which is all the Brashears did, is because of the shape of the flint lens. It's like an upraised arch. And especially in big lenses, it doesn't sag. It's like an arch in a bridge. Where trains go over an arch bridge, it doesn't sag very much. Whereas otherwise, with big, heavy, thick lenses, it can sag. When the telescope is pointed up high in the sky, it's a known factor. Especially like with the Yerkes, these things are heavy. They are really heavy. And they can sag a little bit and change the performance. So Hastings stuck with the flint in front designs from 1880s all the way on. He made a really fine spherical aberration correction, but probably some coma portion. So here's the 2 Frenchmen that I talked about. Clairaut was a very famous scientist in the mid-1700s. He unfortunately died of smallpox not long after he published all his work. His big competitor was D'Alembert, who turned out to be much more famous later on. He contributed a lot to the French encyclopedia. He was a friend of Voltaire's, and he published a lot of very good papers in physics. There's a principle named after him, D'Alembert's principle. Oh, he was much more famous than Clairaut. But it turns out his equations are the ones that are most. Okay, well, he used rectangular coordinates. Clairaut used polar coordinates. And those of you who work with polar coordinates maybe know that it's not quite as much fun or easy as rectangular coordinates. So D'Alembert was a little, I think he was better to do it that way. So anyway, this is all, I put together a basic program to use Moser's equation in a more simplified form. And it was published in Sky and Telescope. This was done back in the day when, I don't know how many people ever used BASIC as a basic interpreter a long time ago. No, you don't use that anymore. The Senate was Fortran, which maybe more of you have heard about. BASIC is still around. It's actually a fairly decent system. I think I still have it one. Anyway, these are not my equations. These are the equations that Moser published, who copied off of D'Alembert. So that's a long history. Anyway, so I published this, and this works. You can design an aplanatic lens with these equations. You have to put in the focal length and the index of refraction. It works. But I can't take any credit for it. done in the 1760s. So what did I do? Okay, and the red numbers here are what I came with was the possible radii for your lens. I hope they are. But if you plug in the numbers into the equations that go way back to the 1760s, you get these radii. They're different. It's quite different, as a matter of fact. But it's going to work better when it comes to coma, much better. The spherical aberration is going to be about the same. And almost never be nothing. But the coma is much better. You would have, these lenses are coma free. So if you ever regrind your lenses, use these ones in black. You'll get. You sure you don't want to do it? Come on, man. Regrind. Okay, no. So again, if you plot the color curve like this, like before, it comes out. You can see there's essentially no spherical aberration in the middle of the spectrum. And the OSC, the offense against the sign condition, is almost zero. This would be a great lens if you had it, but you don't have it. You have something else. But it's still a great lens. I was very impressed with what I saw last night. Keep it. Don't mess with it. Don't take it apart. Don't do anything. Okay, this is what we have. This is the 6 1/4 inch objective that Hastings made in 1879, and we have it. And it has a long history. The history is too long to go into detail here, but it's a wonderful lens. And the good thing about it is that Hastings did not make the cell. He farmed that out to the John Byrne Company. But I don't know what you have, but see those 3 large narrow screws? They are unequally spaced. So if you take this off the tube, you can only put it back one way. Otherwise, the screws don't match up in the screw holes. And the little screws are for collimating. And what you do to collimate it, you loosen the main screws, and then while somebody's looking at it, you play with the little screws and tilt the lens like this, until it gets just right. And we had a guy with a laser do this, and he recollimated. The collimation was a little bit off, so he fixed it up. So this is, I don't know whether your lens has this system of screws. I really don't know, but anyway, this was a very convenient way to do it. So this telescope was in use every Friday evening at our observatory, and it really gives some nice images. Really well. So, these are the measurements that I got from it. And when I was cleaning it, I said, okay, why don't I try to make a stab at measuring the radii? So actually, I built this spherometer to do this. A fairly simple spherometer with a very sensitive dial indicator. And I measured all the radii and I measured the spacing. And this is what I used for the math analysis. So you see, the design is quite different. This is a Fraunhofer kind of design. This is the kind of design that Fraunhofer used for all his lenses. And I knew the refractive indexes because Hastings had published them. So I knew that. And so anyway, so plugging all this into the math to see what I would get. So it turns out pretty good. Now the y-axis is magnified quite a bit, so you can see the very low degree of spherical aberration. It's only a small fraction of 1 millimeter. And the other thing is that Hastings specified that he wanted the marginal rays to come to the same focal point as the red rays and the rays at the 5,000 angstrom wavelength. That's he published that. He said that's what he wanted to do, because doing that would make the minimum of the curve be at the right place in the visual spectrum, like 5,600 angstrom, which is a good place to be. So it gives me some confidence that I measured the radii correctly. Otherwise, this one and the 2 on the side, it wouldn't come out to be the same. So maybe, but the offense against the sign condition is on 0.0001. Very fine lens, which I expect because it was a Fraunhofer design. He never again made a lens like it. He didn't even design a lens because he could make a lot more money working for Brashear and using the parameters that Brashear gave him and turning the crank a little bit to the sun. So he never made another lens like this. This is, I like to think it's the best one he ever made, or even designed. But anyway, so we've got it. So what would happen if I plugged in these radii into my program to see what the program would design? Okay, the radii, the aplanatic radii to the left of the radii that I measured, they're a little bit different, but not tremendously different. And you still get the same kind of color curves, and you still get no cone, 0.0001. I don't know what Hastings did here, whether he referred back to the old French work, whatever he did. The work that Moser published was after he made this land, so he couldn't have used those equations. Whatever he did right. So we're so grateful to have this nice telescope. So here's spot diagrams for this one, again, that Mr. Considine did for me. It's magnified quite a bit so you can see the details. So on axis, the green areas in the middle are the geometric size of the spot, but you can't get it any smaller than the airy disk size, the diffraction limited size, which is the black circle. So this is what you call diffraction limited. Can't get any better than the black circle, but if you could, it would still be better. Would be down to essentially nothing. And what's even better is if you go off axis, it's still good. It's still good, even if you get degree off axis. You can see a little bit on the far left. This one, there's a little bit of inward flare, but if you got to be a full half a degree off axis to do that. And you probably wouldn't see it because it's still mostly with the airy disk side, so you wouldn't see it. So we're very happy with this lens. So I took this picture of the moon some time ago. Zero. Well, actually, it was a larger picture. I took a piece of it. So this is Tycho, which you probably have all seen in the telescope. And for comparison, the little inset shows the size of the municipality where I live, West Windsor Township in New Jersey. And I'm actually on one of the land use boards there. So I have to drive all around town to find out who's doing what, where they're putting their fences, whether it's too high, whatever it is. So I drive all. I like to think I'm driving around a tiny little bit of the greater Tycho. So anyway, it's kind of fun to do this. And then I got this picture of Saturn. And this is back in the days of film. Film, nobody knows film. You don't have film. I had film. I didn't have the stuff that you got. I wish I had. So I had my own little darkroom I set up, and I had my own printmaking. I had an enlarger and all this stuff. So I had to use, I don't know how many of you would know what Tri-X, anybody here know what Tri-X film is? Nobody knows, okay. It's a very sensitive film back in the day for use when you had low light and you needed a long exposure. You had to, and Saturn's not very bright. Saturn's not very bright. So I had the fastest film that I could get to make the exposure time reasonably, because I didn't really have the telescope properly. So I had to use a 4-second exposure with a Barlow lens to get the magnification that I needed. So I got this image of Saturn. You can see the different rings and so forth. So that was back in the day. Nobody uses film. So do you have the setup that you can use to get images with your telescope? Can you use what they call the direct objective, where you don't have an eyepiece? Or you can use eyepiece projection, if you can do that, or put a Barlow in there and get magnification. So I'll be looking forward if you can get some images of the double clusters, things like that. I would really love to see those. So now this is getting off the subject of refractors. This is a huge reflector. This was the Earl of Ross's 6-foot reflector that he made in Ireland in the middle of the 1800s. Has anybody been to Ireland? Been to Ireland? Central Ireland by any chance? This is right in the smack in the middle of Ireland, where the weather isn't very good. It's cloudy most of the time. The Earl of Ross made this 6-foot mirror. It was his own little manufacturer. Speculum glass, speculum metal mirror. It's tin, a tin alloy. They couldn't make it with glass. And he built this enormous thing that's mounted between 2 masonry walls.
All right, make sure it's working.
Okay, I'm gonna need your help now. Thank you. Okay. So anyway, if you ever get to the middle of Ireland, you gotta see this thing. An enormous contraption. And you had a bunch of cables and winches to raise it up and down. It was alpha azimuth, but mostly alpha, not much azimuth. You could swing this thing a little bit between the masonry walls. But he was the first one to make a drawing of M51. the spiral nebula, and he was the first to show really was a spiral. People had thought about that, maybe it is, maybe it isn't. He was the first. So it goes back, and this was the telescope that did it. And he did a lot of other stuff. If you want to read up on the Earl of Rosse, ROSSE, and you see that, and we were lucky that day. It was the middle of the week. There were no tourists there. We had total run of the whole place. So we saw, yeah, huge estate. Great place. Please go there if you ever get a chance.
So the piers are north-south,
Sorry?
piers?
The piers are north and south.
North and south.
Yeah, so it's on the meridian.
Thank you.
Yeah, yeah. So it can only swing a little bit, and he needed two people to raise this thing. They had a winch set up, and they had two big cranks to raise it up and down. So he would say, raise it up a little bit, they would raise it up. And he had these galleries on the side. You'd get up in these galleries and lean over and get, it's a Newtonian, and you lean over and get the eyepiece and see this stuff. But with that, when the weather was clear, like one night out of every 10 in the middle of Ireland, he would get up there and do this thing. So you got to see this thing if you ever get it. That's a telescope. That is a telescope. Uh-oh, I can't advance it again. I need help. Help is on the way. Okay. Oh, nice. If you can make it advance. Okay, now here's the good part. This is what you're going to see pretty soon. I hope. I've seen 3 of these things, and you probably, those of you who are in astronomy know about the Saros, the 18-year, 11 days cycle of eclipses. Well, if I see this one, we're going to Ohio next month. We're on the path there. This will be 3 Saros after the one I saw in 1970, which is that little red dot over right in here. That's where it was. And I'll show some pictures of that. So with the Saros, after 3 Saroses, an eclipse path comes back almost to the same place it was 54 years ago, almost. It's because each one is 18 years, 11 and 1/3 days, give or take a little bit. So 3 times that, you get a full day. And so it's almost in the same path, and it's just shifted a little bit. For one thing, the Earth is a little farther away from the sun in April than it is in March. So you get there, the sun is smaller, so the moon looks bigger, and so you get those wider eclipse paths. And so you're going to have a nice wide eclipse path. Okay, you all got to go with this. Rain or shine, whatever. I hope you see it, and I hope I see it. So it'd be nice to see the 3 Saroses later. So that's what it's going to look like. So in 1970, I got this picture with film, again, Kodacolor film. And this was at about sunspot maximum. So this is why the shape of the corona is like that. And I think that, aren't we coming up to sunspot maximum again pretty soon? So I think if you see the corona, it'll probably look somewhat like this shape. It's different if it's a sunspot minimum. It's coming up more equatorial. I have a picture of that. So after taking this shot, a few seconds later, I got the diamond ring. And this is what you will see also, hopefully. It's called the diamond ring because you can still see the inner corona, the little circle on the left. And then a huge, it's a blinding flash of light. It's like a spark. It's the edge of the moon, and it certainly goes, it'll blind you to look at it. And the little spikes that you see are just an artifact from the iris diaphragm of my film camera. Just reflect. It doesn't really look like it. That's an artifact, but it does. You can see the diamond ring. So that was 1970. And 2 years later, we went to Canada, New Brunswick, Canada, to see another total eclipse. And it was high, thin clouds. Didn't do much about that, but I got some images. Still a very nice eclipse to see. And I got a bit of a close up here. I use a telephoto lens, a 400 millimeter telephoto lens. And hopefully you'll see these, the prominences off the edge of the moon. These things, one of these things would swallow the entire Earth. But fortunately, they're not very close, a long ways away. But you'll see them at the edge of the moon. Hopefully you will. So that was 1972. So here we are, just back in 2017. And the guy in the orange jacket is my brother Robin that we're just talking to try to get this video to work of the eclipse. So this was like 6 minutes before totality. We were up on a hill very close to the center line. We had a perfect day. It couldn't have been better. Clear blue sky. And the one thing that's interesting is how sharp the shadows are, because the sun is just almost getting down to a point side, and the shadow, it's not like the diffuse shadows you normally see. This is a striking effect. Shadows are almost razor sharp. So this was 6 minutes to go. And the ground has already started to change color. So hopefully this video is going to work. My brother took this video looking west towards where the shadow was going to come from. The ground changes color. It's rather spectacular because at the edge of the sun, you start to see the chromosphere sun, which is more the hydrogen alpha emission line. And the ground will get kind of orange. It's really spooky. And you get light flashes from Bailey's beads. You go peep, there's all kinds of flashes of light happen. Then totality comes up. So now, okay, here, I need technical assistance to make this video work. Sound, if we can get it. You have to be a little patient. It takes a little while for the thing. Okay, sound.
It should work. Just getting. Two four is what we're getting, all right? So.
Oh, here we are. Okay. Okay, the shadow is going to come from the direction of that barn at the distance. So you can see the umbra in the sky. Okay. So there's some sound effects, but driving will start saying, you're going to see the ground change color. Okay, you're starting to see. People are starting to cheer in the background. Totality is coming. Oh yeah, this is what happened. Now watch, the ground is going to get flashes of light and the ground is going to start changing color. But we should be getting some effects here.
Here it comes.
That's my boy, that's my brother. Now watch what happens.
Getting different.
See, the ground is going to change color. If you look at this, that's the chromosphere. Scared the daylights out of the ancients.
Yeah.
That's what. Oh, the end of the world.
Wow.
I hope you see this. All right, thank you very much. All right, okay. Well, oh, he's still with me, he's still going. Oh, he's got more of the video.
It's a 5-minute
That's
video.
all right. Oh, then we need to go ahead. Okay, anyway, that's the.
Love the Halloween.
Yeah, that's what's, everybody cheers and scream.
Are we all gonna howl?
So, we need to go. All right, I'll go back to, oh, that's okay. Okay, this is, my wife took this. Yeah. My wife took this picture in totality. This is what you see. It's dark, but then that's the moon's umbra in the sky. And around the edge of the umbra, it's still lit up. See that. So, and at this point, everybody. Yes. Yeah, so, and then, but it only lasted 2 minutes. And this one, if you get closer to the center line, it'll be more like 3 minutes. But, and I told Ben that if I see it, I'll be half an hour, 45 minutes earlier than you see it. I'll call him up, tell him if it worked or not. And I just hope you guys see it. All right, so I got this picture here. I called it the cat corona because I see the two ears on the top and the chin at the bottom. So I quoted William, the tiger, the tiger. So you would get something like that. But the coolest thing about the corona is how fuzzy it's the fuzzy filaments that and the outer corona. It's really spectacular. It really is. The inner corona is bright, and in this photo it got washed out, but I caught the outer corona. So that's just a spectacular sight. Okay, so I'm just about through. This is just for future references, the references that I talked about. And I just want to say thank you to all the people that helped me, Ben and Michael, and at Yerkes, Dr. Amanda Bauer was a great help to me, trying to look up files on the glasses. Dr. Richard Crone at the University of Chicago was great help. And I called the Brashear Association in Pittsburgh, see if they could find any records of the glasses. They looked and looked and looked. They had all the records of the Brashear Company, but they could not find any reference to these glasses. Mr. Snyder, credit for trying to help. And John Briggs is a guy who's done a lot of work with Brashear lenses in the past, and Matt Considine, my friend, who did the spot diagrams. So I won't go through the next, there's a few more slides on how to do ray tracing if anybody ever wants to try it. It's in the PDF, it's very boring, so I won't go through that. But I basically stuff here like that stuff. But what I did to check it, I checked my ray tracing figures with the Hastings' own figure, and it jived exactly. So for both the marginal and the paraxial. So, all right. Well, anyway, that's the end of my talk, and I thank you so much for your attention. And I hope you see the picture. You're going to have expeditions, right? You got to have buses going up there. You're going to Rochester, okay? Even if you don't get to Rochester, if you just get somewhere, if there's a traffic jam, which may well be. What? Oh, we had a terrible traffic jam after the 2017. Nobody could get back to the Portland airport. It took them hours and hours. Fortunately, we were going in the other direction to my brother's house. We didn't get it. There's a terrible traffic jam. But if you can get anywhere inside the shuttle, you're in for a real treat. Okay. Okay. Well, anyway, if anybody would like to have some questions, I'd try to answer them.
Let me say real quick that microphone for this room is a more sensitive microphone than we have ever gotten from these lectures before. It should, the microphone's up there, but it should pick up your voice no matter where you ask a question from. So we won't be running the mic back and forth this time.
As long as you speak loudly and clearly.
Okay.
Don't whisper.
Yeah.
This 6 month is in use weekly. The observatory that you go to, I also live in New Jersey. I was just wondering what that is.
Oh, so this is in the observatory is in Washington Crossing State Park in New Jersey. Okay, it's actually close to where Washington crossed the Delaware. Okay, you heard about that? There's a state park on the New Jersey side, which is where we are, and the state park on the Pennsylvania side. And the state park is state land. But we had a guy who worked at the planetarium in Trenton, and he had a good connection with the state. And he convinced the state to lease us about an acre of land in the state park. So we have that on a 25-year lease. Coming up, it's actually been renewed once, so we hope to get it renewed again. The caveat was the state said, okay, 2 things. First of all, you got to have a restaurant. You got to put in plumbing. What a hassle that was to put in plumbing. We had to do that. Otherwise, we couldn't have the public. And the second one was that we had to say that we would throw this observatory open to the public at least 16 times a year. We do it in the summer. We do it even more than that if we can arrange it. And on Friday nights, just like you do, and if the weather's clear, it was published on our website, and people come and they can use the Hastings telescope as well as a 14-inch that we have. And we have, it's fully computerized. They all are. And so I was really thrilled to see what you have, the wonderful clock drive. The cog wheels and the pendulum swing. So the things have advanced a little bit. You don't want to modernize this one, though. This leave it just like it is. It's so picturesque. So the one we have now is fully computerized. You just enter on a laptop the object that you want to see. The thing swings around automatically. Hastings would have loved it, but he's not there to see it. So we can even get it to reverse the side of the pier. So that's just, and we open it every Friday night if the weather's good. And we see all this stuff and we get, it's especially fun when children come out. So children come out and even the adults, we put Saturn in there and they look at Saturn and they say, oh, you're not looking at Saturn, you put a painting.
You get
You're
that?
looking at the,
Yeah.
no, it's fake, phony. We get that all the time. And then I tell them, the kids, that I say, you know, the Earth isn't standing still. We're running around at 18 miles per second or more. And they say, get out of here. I can't feel the Earth moving. What do you mean? You can't tell me the Earth is moving? Yes, sorry, it is. But they don't believe it. So it's wonderful the way the kids react to telescope. You get small children coming out, or you get the same kind of stuff. Yeah, it's fun, isn't it? And you teach them some astronomy, and they say, wow, wow, so good. Okay, well, anybody else have a? Yes, sir. Yes, sir.
So, two questions on the eclipse that you observed in 2017. I couldn't quite see in the movie, but did you see any of these shadow bands?
No, we were looking for that. We didn't see any. Now, there's various theories about the shadow band. Some say it's just an atmospheric effect from cooling of the air or something. We were looking and looking, but we didn't see the shadow band. I would, if you get a chance, look for them, because it's a very interesting effect. We did get these flashes of light with Bailey's beads, because mountains cover and uncover, and you get sudden flashes of light. It's spectacular. But you can't see it really unless you look at the ground, but you want to look at the sky. That's the thing. You want to see the last stages. But if you want to see the effect on the ground, look at the ground. Or you get a video like my brother did. You get these bright, these flashes of light, and then the ground changes color.
So you can see that best looking at the ground?
Yeah, if you want to, yeah, if you get, you see, we had a big wide open field with no grass or anything. That's why we could see it. If you have grass or something like that, you might not see it as much. So we had a fallow field there. So that's why we got those nice color effects. You'll see the color effects anyway. But to see that, you have to look at the ground. But you don't want to be looking, you want to look at the sun.
Yeah,
Right?
the instinct to look up.
So what I was trying to get, and I did a video too, similar to this. I was trying to see the actual approach of the shadow, like a wall, but it comes so fast. It comes at like half a mile a second, which is the rate of the speed of the moon in its orbit. It comes fast, and before you know it, it's on you, and all of a sudden it's dark, and then by hoops and hollers.
Descriptions I've seen of shadow bands in a few places, often were when people on the tops of mountains.
Yes, that's right.
And if you could look down at the clouds.
You see it. Yeah, you see that.
In those places, description.
Yeah.
I'd see shadow approaching.
We were- Oh, yeah, if you're up high, you can see it much better. Well, we weren't up high, but we were on top of a hill, but we weren't elevated that much. So anyway, I don't know if you're going to be up on top of a hill or in a public spot or something. I have no idea, but get the clearest view you can. Do what you can, even if you have to trespass on somebody's land, they won't care. See, it's funny, when we had this one in 2017, there was a police officer parked on the road to keep order in case whatever. And a lot of people parked on the road. We were up higher on the hill. And so just before totality, the police officer turned on his flashing lights. Everybody would know. And so anyway, you can see that if you just get anywhere in the shadow, you can park for a couple of minutes. Nobody's going to bother you. Get the best place you can. Even if you have to go out in the countryside, just park on a road, and nobody's going to care. And get what you can. Get the best spot. So, yeah, like I say, even if you have to trespass on somebody, they'll be out there watching too. They won't care. In fact, they'll like the attention. So good luck with the eclipse. And I won't be serious. You got to go with that.
I had a second silly optics question.
Yes.
Back to the beginning part of your talk, but I should know the answer to from my optics class. but
Okay.
A long time ago, so I forgot.
So I hope I can answer it.
So you explained nicely how you calculate.
Yes.
In an ideal world, you could flip the lens backward. You could just
I
turn the
did
whole thing
that.
around 180 degrees. Would it still work?
No, I did that. I did that. I wanted to see the effect. the Hastings lens. Okay, and I knew in advance it would be bad because the aberrations come out terrible if you reverse the lens. I did it. I put the flint first.
In the computer,
Yeah. So normally this is a crown in front.
right?
I flipped it, so the flint was in front.
Yes.
It was awful. It was just horrible. And so the spherical aberration was terrible because it depends on which direction the light comes through to get the best. You cannot flip a lens like this. You cannot flip it. You got to keep it the right way. You get the same focal length. You'll get the same focal, but you won't get the same aberration.
Aberrations are different.
Very
depending on
much
the
so.
direction.
Right.
What about the chromatic?
It'll change that too, because it depends on whether the crown in front, there's a certain dispersion that you get and the flint cancels most of it. If you put the flint in front, unless you design it right, it's going to be different. But they both can work perfectly. If you
But
design,
have got different parameters.
yeah, you have different. Well, you can't just flip a lens. It's not going to work. It's too asymmetric. Because the curves are so different. But I did try. I was curious.
Yeah.
I said, look, the ray tracing is telling me it's going to be no good. It was awful. It was so. So I hurriedly put it back to ray. So anyway, yes, I did try that. But do not try this at home, okay? As they say. Especially with the old thing, do not try this. Okay. Anybody else have some question? Yeah, man.
You mentioned that the coma, when you looked through our telescope last night, you mentioned the coma was much better than you were expecting.
I couldn't really see it, but if you had, I couldn't see any of it. Doesn't mean it. Maybe still, my eyes aren't what they used to be. But if you can get a photo, if you can get a wide field photo, and try to enlarge it, you may or may not see it. Now it's not terrible. I mean, if it's there at all, but it's enough to mess with parallax determination, which is what the professionals did. It won't bother you visually. It really won't. And in most cases, you're going to be using it for the reach. But for parallax, that's what the professionals got paid to do. It really hampered them. It really hampered them. There's a story about an astronomer called Pete Van de Kamp, who worked at Fuertes Observatory. He thought that he had detected, you know about this story, he thought he had detected an exoplanet around Barnard's star. Because he got pictures of it and he saw Barnard's star weaving in
Those were decades.
yeah, over decades. And he published it. It turned out to be an artifact, an instrumental artifact. It wasn't really what he thought, because he was bothered by the coma that they had, which made it uncertain. And so, but he kind of staked his career on that. And so finally somebody said, no, I'm sorry, Dr. Van de Kamp, it's not really that way after all. But he, back in those days, they were really looking for exoplanets much closer to the Earth. And Barnard's star was a good candidate. It's only like 9 light years away or something like that. It has a high proper motion too. Is that correct? I think Barnard's star, and whatever.
For many years.
Yeah. Yeah. Anyway, he thought he thought he saw the primary wiggling a little bit, and he redrew pictures, and he had all these equations. Turned out, sorry, but true. So be careful with coma. Visually, it's not going to bother you. Besides, you're looking in the center of it, not doing parallax. In the center of the field, this telescope is.
I think we're still interested in quantifying the edge effects wherever we can.
If
I'm
you
also
can.
curious, from you were looking through the double cluster last
I
night,
couldn't
are
see
there any parts of your provisional analysis that
It
you think
looks
are,
darn good to me. Looks
Okay.
darn good to me. But theoretically, it's probably there, but maybe you can't see it.
so you
probably-
think based on that look, you would say the provisional analysis holds up well?
I hope so. I hope so. I mean, if it doesn't, I'll eat my words, but you still got to measure the radii. Even if you could just measure the outer radius, if it's close to this, then I'd feel a lot better. But whatever it is, it is. I don't know if you can arrange to have this measured. You don't have to take it apart. If you can get up there, and even if you have the telescope about like this, you don't want it horizontal because you have to let the spherometer rest against it. And it has to do so. You get a lightweight spherometer and put it very gently on the glass and see if you can get a measure. That's a okay undergraduate thesis project.
Okay.
Measure R1 and see what comes up. And if you find out, let me know, please let me know, and I'll adjust everything back again. So, but please don't take this thing apart. Don't do anything else. It's so nice. And many happy years with this thing. I know you're out there every Friday night, right? But you have, but you're all undergraduates, right? So you're getting fresh blood every year. You have to teach people how to use fresh blood. You have to teach people how to use all these complicated. Our observatory is duck soup to use. We have it computerized and a roll-off roof, but you got to set up the motors and get it working. But it's great that you guys do this. And so please keep it up. You've got a wonderful thing here, and a good teaching tool. And I talked to Ben again about lunar occultations. I used to time lunar occultations all the time back in the day, because these are valuable for getting details of the moon's jagged edge, the mountains, and also some other purposes. And what they call the International Occultation Timing Association, or IOTA for short, is still active. And the same guy is still running it. The same guy who was running it years ago. They still want timings of occultation, even though a lot of it's obsolete now because of lunar laser ranging and satellites going around and measuring the mountains and all that. Nevertheless, when the moon suddenly covers, especially when you got a crescent moon in the springtime, the dark limb of the moon goes across a star. It looks like the star vanishes, and it's not quite, because you get two effects. Number one, the star has a certain angular diameter, very small, but it's there. You get diffraction effects. You get Fraunhofer diffraction, far field diffraction. And we saw this. I had a friend in the astronomy club who had high-speed electronic equipment. He came over to my house and they set this up. And we set it out on an occultation. And you get the diffraction fringes, like this, very quick, as the star. He was able to record that. So that's another undergraduate thesis project. Get some high speed. I'm sure you must have people here who can do high speed electronics and get videos of it. Just videos of this, of the diffraction effects of an occultation of a reasonably bright star. These are published ahead of time. I think I sent you a link with the IOTA. You can get local predictions of occultations for your exact location. You specify the latitude, longitude, and elevation, and it'll give you what star is going to be occulted, how bright it is, and what you can expect to see. So we could do the same thing simultaneously in Princeton. The star won't be occulted at the same place or at the same time, but I thought of a project. Again, you get your high-speed stuff. You do it there, and we do it here, on the same star, the same evening, and compare the results. Because we could probably have somebody make, if you can get something made, simple project, right? No, not simple, but undergraduate thesis. Okay, get high-speed equipment and get reporting of the diffraction fringes that you see when there's an occultation. And if you're very lucky, you could even figure out roughly the stellar diameter of the star. It's been actually has been done in the past, and that's really nice if you can do that. So anyway, so I've got these ideas with this. I can't do it. You guys can. You got a good engineering department. Yeah, I've heard about it. You got a good engineer. Yeah. You got electrical too, right? Yeah, all right. Do it, please do it. And then send us the results, or send us the plans for it. And we'll have one made. Just idea. Anyway, so anybody else? Something? Well, if not, thank you so much for your attention. I'm very glad to come here, and I really thank Ben for helping set this up.